Let's get started, everyone. So welcome back. So I fixed my technical issues, and so we can start on time today. Apologize for Tuesday. So also on Tuesday, so we covered a lot of material kind of quickly. It was kind of the last lecture in a section, and there's a lot of cool stuff I want to explain. And it was like, I think it was like a lot of stuff on, on the iPad for a lot of people. And so someone suggested if we could have a small break in the middle of the lecture. And so I'll try that today. We'll see how it goes. So if you feel like it's a good time for a break, and, so you can wave me, I'll try and put this in the lecture, but so we'll see how that goes. So let's see. So we finished most of the section on probability, the probabilistic perspective. This was mostly to help you understand the core concepts of how, so how you can start with the noise model and get to the sum of the squared errors. And also, as you get more and more data, understanding how why as you get more and more data, you get a better and better estimate. And so the basics of how to formalize that. So what we did so far has been in basically, one dimension, right? So we looked at just, so each data point was just a single value. What you typically want to do in data mining and machine learning is you have multi-dimensional data. And so like there's this kind of a data set I've been working with that's often 300 dimensions, right? And so kind of the tools you need to think about in these higher dimensional representation of data. If you have a kind of the representation of a person, you might have their age, their height, their weight. You have a whole bunch of different characteristics of people. How do you do analysis that aggregates all of these things together at once? I think for the most part, it turns out it's not that hard to do it if you use the language of linear algebra, right? So the next section of the course is reviewing linear algebra. Not all of what's in a linear algebra course, just like we didn't review everything in a course in probability, but I'll review the kind of the core things you need to think about and operate and define algorithms on data in high dimensional data instead, right? So that's what this section will be. And then we'll start getting into the actual kind of analysis techniques. In order to write any of these down, I'll need to write them down in linear. So using linear algebra. So some of the things you may or oftentimes not seen in a linear algebra course, but you may have seen will show up as core operations within here. But those things we will review as well. So the first quiz we talked about. So Tuesday, the first homework was due on Tuesday. I hope the first homework went okay. There are a bunch of good discussion on the discussion board, but that kind of slowed down the last few hours before the deadline, which is good. If it had been kind of peaking at that point, that would have been trouble. So I take that as pretty much a good sign. So we'll see. The late. Again, remember, you can turn in homework late for a penalty. I think almost everyone's turned in the homework so far, but after the late period expires, which is after 48 hours, we will post a rubric online and we will start doing the grading. The rubric will also explain what the answers were to the questions, right? So you'll see that once we post the rubric. That'll be kind of after the clock strikes midnight, or so something like that. So, okay, and then homework 2 is now out. Yeah, so it should be linked off of here. This is going to cover the last section on so convergence, and then on the basics of using linear algebra. You're going to get examples applying those bounds we saw the last couple of lectures, right? So I know we kind of went through it fast. We did some examples, and for you to learn it, you'll apply some bounds. This is just some things where you'll have to calculate these bounds, and then this one requires a little bit of thinking. So the second one, it's less of a direct application and more of, okay, you have to think how to apply them in slightly more trickier scenarios, but give you a kind of a window into, challenges you might get when you use them in the wild, which you might see in a machine learning or the data mining course, or kind of in stuff beyond that. Okay, and then sorry about that. Then there's some questions on linear algebra. These you might be able to start now if you've done a bunch of this stuff before, but otherwise after the next lecture or two. So next week, the first one is on kind of just questions of how do we do stuff with linear algebra. The fourth one is intended for you to use Python to do this. Python has a library that makes it pretty easy to do a lot of these things, and the intention is you to kind of do some basic operations in here, okay? Just to force you to start using this, and then throughout the rest of the course, we'll use it in slightly more kind of complicated ways. I will give you probably Tuesday a kind of a short preview of how to do this stuff in Python. It's with Colab, it's really pretty straightforward. Okay, so let me say in terms of the homeworks, probably the first and the second homework are going to be partially review for a lot of you. For others of you, like a refresher. They're probably a little bit less challenging than homeworks 3 and 4. Homework 5 at the end of the semester is probably not going to be as so challenging again. So I don't expect this homework to be super challenging, but there'll be more kind of new stuff where you're building knowledge we've had throughout the semester that's going to be integrated into homeworks 3 and 4. Okay, so just to kind of prepare yourself for kind of the level and the homework. You'll get homework 3 out before fall break, so you have a bit of time to spend a little bit more time on that if you want to, or you don't have to work over fall break either. There's enough time, it's supposed to be a break. So, okay, great. Any questions on the schedule where we are? All right, this is kind of a transition point in the semester. So, okay, here we are. Okay, so linear algebra review. Again, I'm going to cover a lot of material quickly in this lecture because it should be a review. I think almost all of you have probably had a linear algebra course, but hopefully I'll give you a different perspective on how to think about the linear algebra. Particularly, I like to think about things geometrically, and linear algebra, in my view, is about using vectors and matrices as the base kind of object you're dealing with. So a vector, I'll usually write V as a vector, sometimes U, something like that. Eventually, everything in this class will be a vector. Okay, but this vector will have a set of elements. So let's see, this is V1, V2, up to VD. Okay, so this would be if it's in these rounded parentheses, that means that it's an ordered list, which means the order of these things are important. If I swapped V1 and V2, these is going to be so a different vector, okay? And this going up to D means that it has, so D elements in the vector, and we'll say that this is gonna be an element of, so it's in the space R, so D, this is a blackboard bold version of an R. So it used to be, if they wanted to write something in bold on the blackboard, they would write an extra line next to it on the left. But then this notation is inside of, so like LaTeX, so you can make things look like this. So this is like the real numbers, and there are D real numbers, and the order of these matter, right? So that's what this notation is. And this is, slash in, right? So it's an element of this space of D real numbers inside the vector, okay? And so if we have a vector, there are kind of two ways to think about this vector in the sense of like linear algebra. You can either write it, the default will be that this is a column vector. In most cases, the default is going to be a column vector, VD, or you can have V transpose, which means it's going to be a row vector, V1, V2, up to VD. Okay, so and so whether it's whether it's a column vector or a row vector is mostly not going to matter, okay? Some cases this is more important. I'm gonna I will let you know if it matters, whether it's a row or column vector, but I'm mostly gonna ignore this. The reason is, if you're programming this, right, if you're a computer scientist, you think about this as an array, right? It's a length D array, and it has got D slots in it, and you're storing D, real values, whether those are floats or doubles, right? All right, and so it's just going to be an array, and whether it's a column vector or it's a row vector is not going to matter in most cases, right? In fact, Python, as we will see, it stores them the same way. It stores them as internally as just an array, and if you print it out, whether it's supposed to be a row vector or a column vector, it always prints it out as a row vector, because the row vector can print on a line, where column vector, it kind of takes up a lot more space, right? So it tries not to distinguish these things, and I will try and use notation, and we'll learn this throughout the next few lectures, that makes it not matter whether it's a row vector or a column vector in most of the time, okay? All right, so this is a vector, right? You just store it as an array, okay? So the other thing is going to be a, the other element, important thing, as I said, is a matrix, okay? And so for a matrix, I'll typically use A, okay? And often we'll have a matrix, it'll change depending on the situation, but if I don't kind of say otherwise, it'll often be N by D, right? This is how we store this. We're often going to store our data inside the matrix. So I'll say that A is in the space of the real numbers of N cross D, right? And so what this means is it's going to have N rows and D columns, okay? And I can think about this matrix as a let's see. So often as a stacked set of these rows, A2 up to AN, right? So what's happening is so this matrix is going to actually contain a bunch of these entries, A11, A12, up to A1D. This is the first row of the matrix here. It goes from 1 to D, and that corresponds with this A1 vector here. Was there a question?
Yeah, so I guess we're doing, these are row vectors for this.
Yeah, so in this case, it's so it's a row vector. Yeah, right. So I've kind of written them in the way so it makes sense as a row vector. Like I said, most cases it'll hopefully be apparent from the situation. And I'll okay, and then it's going to have, but it's going to have a whole bunch of these stacked up. So this is the second row, A1, A22 up to A2D, up to A1N, A2N, up to A, no, I've messed this up. Okay. A1N, A2N, up to A, nope, okay. This one I did wrong. This should be A2122, yeah. And then a N1, N2 up to ND here, okay? Right, so it's gonna be filling up this array, right? And so okay, so each, again, as I mentioned, each row here corresponds with a row. I can think of this as a row, so A1. Okay, so I'll try and if I'm using a vector, I'll try and typically use lowercase value of the letter. And if it's a matrix, I'll use like the uppercase. And if I have an element of a matrix, I'm indexing both the row and the column, then I'll use the uppercase and I'll use so the index that way. It's typically the notation I will use. If I do something different, I'll try and explain that. All right, but I can think of it. Okay, so there I could also write this, right? Think of this as a bunch of the column vectors, right? There's a column vector of length n, another column vector of length n, and there are going to be d of these column vectors of length so n. We're going to switch between these occasionally, and I'll try and explain that. But I prefer thinking about it this way for the for the following reason. Okay, so typically this vector is going to be a data point, and so then I'm going to say I'm going to have n data points here. Okay, and I'm just kind of stacking them. Each row is one of the data points, and I'm going to have n of them. Remember, we typically used n when we said, okay, as the number of observations n goes to infinity, in the central limit theorem, then stuff starts to aggregate, and this happens in the matrix. The matrix gets so it becomes taller. It means have more rows, and these are data points in in RD. So this is n data points in RD. So D will often be the dimension of the data points, the number of attributes we have of something. Okay, we'll deal with other matrices that have intermediate representations, and so this will change, but our default thinking about input matrix as our data will often be n data points in D dimensions, and what n and d will change based on the situation here. Okay. So one other thing I like to think about with respect to vectors, okay, is that again, these are often these d-dimensional vectors, and I like linear algebra because it allows you to generalize concepts to kind of arbitrary high dimensions. I can make d 300, and it works basically the same as if, so D is equal to 2 in most cases. I will try and draw pictures when I can that give you the right intuition, and if that intuition breaks down, I'll try and tell you that this two-dimensional intuition is going to give you maybe the false interpretation here. But if we have so vectors in 2D, so D equals 2, right? So now this is R2. Now I can think about vectors in, so let me change this a little bit. I can think of them in a couple of so different ways. The first thing to point out is that, so let me say, so I could think of vector A1, that this could be one vector up here, and I can write it in terms of its coordinates, the x and the y coordinates. So the x coordinate might be -1, and the y coordinate might be 3. Right, so I think of, it's about, if this is the distance 1, then maybe this is 3 steps up, or maybe it's 3.5. Okay, so maybe that's one vector. I can draw another vector that say this is A2, and this is equal to 1, 1. And then let's do a third one on here. Maybe A3, this would be, let's say, 4, 0.5, right? So if I'm in 2 dimensions, the values represent the x and the y coordinates. If I'm in higher dimensions, right, I've got a third coordinate maybe that's coming out of the plane, and then there's another coordinate, and these are just the coordinates of these points, right? So these are vectors as points. Okay, but in some cases, it's important to also think of vectors as actually the, so like the arrow, right? I can think of drawing the arrow, right? And this is the arrow from, from the origin. Right, this is equal to, sometimes you write it as like a bold 0, 0, 0. So it's a 0 in every coordinates, okay? And I think of it as the arrow from, 0. Okay, so sometimes you write this as, for instance, as A2 is actually the difference from the point, maybe the vector A2 is A2 minus, so the origin, right? So if I subtract the origin, we'll talk about matrix addition or vector addition and subtraction in just a few minutes, right? But then if I subtract out 0, I get this vector. I get the vector from the origin to this point. Okay, so you can think of it either as the points or as the vectors from the origin, and these, again, from a computational point of view, they're stored the same way. They're stored in an array. If you take a class in physics, sometimes they make a big distinction between these two things. That a point, you have to think of a point separately. It's a different type of object than as a vector. In this class, they aren't going to matter. In fact, in some cases, we're going to, so in at least one case, we're going to write down an algorithm that uses both representations, and it uses a trick that a vector and a point are the same representation, and I can swap their roles in terms of the meaning, and the algorithm only works because they're both kind of arrays of size d, right? So actually, we're going to kind of purposely abuse this. If you're kind of from physics and you're taught to distinguish these, we're going to try and not distinguish them. Or again, to simplify, they're just vectors, and that just means an array, a point, an arrow from the origin. Those are all the same thing. Okay, and then if I have, a matrix, right? The matrix A here would just be A1, A2, A3, right? I could think of these row vectors, and I can stack them on top of each other. right? So if I stack these on top of each other, this is the matrix. The matrix is then a set of points, right? This is the way I would think about it. There are other ways you sometimes need to think about it, but in general, we'll be thinking about it if it's an n by d matrix as just a set of 3 points. So, okay. I guess something I didn't specifically talk about, I mentioned this earlier in the semester, someone asked me about, so the transpose. Let me just say this quickly. This is an operation written, we'll write it as an uppercase T that's in in like the superscript. You can do this with a vector or a matrix. I did this with the vector here, right? So I've changed it from a column to a row vector. That's what the transpose does for a vector. If I write it for a matrix, right? So if I start with the matrix A1, A2 up to AN, right? As these are a bunch of rows, then the matrix transpose is going to be equal to A1, A2 up to AN, but now these are going to be so column vectors. They're in the same kind of order as they were before. Top to bottom becomes so left to right, right? So left to right becomes, it's backward. The top to bottom becomes so left to right. This matrix is an element of Rn cross D, if these are d-dimensional vectors, and this one will be an element of R D cross N. Okay, so these, if N and D are not the same, these are not in the same kind of, I can't draw them in the same space, right? Or I can't think of them as being from the same space anymore. But really, it's just a different representation. Again, how does a computer store a matrix? If it's a dense, I mean, if there are some other fancier ways, but if it's in memory and it's a dense matrix that has all the elements in there, it stores them as like a set of rows that are just concatenated together. All right, so it reads the first row, then the second row, and it stores them in order in the memory. And if I note that it's transposed, well, I would probably just kind of keep track of the N and D values, and then I would have a bit that it's transposed, and I would have to access it in a way which is different. Okay, but I don't necessarily need to change the how it's stored if I do it as a transpose. Okay, it could be stored exactly the same way internally. So again, from a computational point of view, it doesn't necessarily matter, but sometimes for some operations, we'll need to pay attention whether it's A or A transpose. Okay. One other sort of, all right. So one kind of important place where these linear algebra is helpful is if I have like these linear equations. Okay, this is you can write down linear algebra. It gives you kind of a very compact way to write linear equations. This is part of why it's called linear algebra. I mean, this is a main reason. So here's an example. So if you have 3x1 minus 7x2 plus 2x3 equals minus 2, right? That's one equation of 3 variables, x1, x2, x3. Right, so and I can write another equation of the same variables. Okay, 6. Okay, so I've written this out. It took me there's a lot you have to write this out. It's got 2, so this has N equals 2 equations, and it's got D is the number of variables. Okay. And so what I would like to do is to write this in a compact form as AX equals B. And what I'm going to do is this is going to become my matrix B. These variables are going to become a vector X, and then these coefficients are going to become matrix A. Okay. So what I can do is I can write so B is going to be -2, 6 as a vector. Right. So I have two equations. It's going to be a two-dimensional vector. X is going to be a three-dimensional vector. And then, right, so this is an element of R2. This is an element of R3. And then I'm going to write A is going to have it's going to contain all of the coefficients, 3 minus 7. Typically write a space, -7, okay. 2, -1, 2, so -5. Okay, now I've written A as this matrix. And now I can write it as this equation. The matrix A has all the coefficients times this vector X of the variables is equal to B, which is the right-hand side of this equation, right? So I get this very compact form that I have, and then there are ways to solve this equation for X. Well, in this case, I can't totally solve for X, but but you can solve for some solutions for X, right? Or the space of solutions for X, right? So this kind of gives you a very compact form to write these things. Okay, but I've done some kind of stuff here. I've effectively I've multiplied A times X, and I need to be able to do things like to work with this representation. There's some very basic things I need to be able to do. I need to be able to add. Addition will give me subtraction because I just put a minus sign front. I need to be able to multiply, and then I'll need to be able to divide sometimes. Well, the rest of today we'll talk about adding and multiplying and kind of dividing through the inverse. It'll be in the next lecture. Okay, so hopefully I'll give you kind of some pretty simple views of this. Okay, so addition is very straightforward, right? So if I have two elements, X and Y, which are both in RD, then Z equals X plus Y. This is just going to be let me write X and Y, right? So this is X1, X2 up to XD equals, and this is Y1, Y2 up to YD. These are both in RD. Then X plus Y, Z is just going to be, adding up the elements. So it'll be X1 plus Y1, comma, X2 plus Y2, comma, up to XD plus YD, right? And this will also be an element of RD. Okay, so if I'm adding together vectors, they have to be in the same space. They have to be in the same, they have to be the same dimensional. If X was 3-dimensional and Y was 4-dimensional, I don't have a way to add these together. Okay, so the dimension has to match. The dimension must match. And if I want to subtract them, it's the same way. I just put a minus sign instead of a plus sign, right? If I do a minus here instead, then these just become minus signs instead. Okay. Okay, and I can also do this with matrices as well. Let's say I have A and B they're both in Rn by D, then I can get a matrix C I can just write A plus B, right? And so this is just defined, so the elements Cij is equal to Aij plus so Bij. I just take the same elements that I have that correspond with each other, just add these things together, and subtraction is the same way, right? So if we write down a small example here, we had A from our slide before, 3 minus 7, 2, minus 1, 2, minus 5. This is A. It is, so what is the dimension of A? Yeah, so it's 2 by 3, right? It's 2 rows and 3 columns. And then B, I write 2, 5, 3, 4, 8, 1. And if I add them together, C is going to be, let's see, 5. I've added together 2 and 3 to get 5 there, right? Negative 7 plus 5 is minus 2. 2 plus 3 is 5 again. Minus 1 and 4 is going to be 3. 2 and 8 is 10. And minus 5 and 1 is minus 4. Right? Okay. So this is C. I've added together the same corresponding elements. Okay. So addition, very straightforward. There's one nice way to think about this for vectors. Let me just draw a picture here. If I have 2 vectors, and again, I'm going to think of them as X, and this one as Y. I want to add these together. Well, one thing I can do is I can take this vector Y and add it to the end of X, right? The coordinates match. So I can draw this vector Y here. Let me try this. Right, so this is Y. And actually, this point is X plus Y here, right? Because I first walked along X, and then I walked along Y, and I added the X coordinates together. This is X's X coordinate, and this is Y's X coordinate. I added them together, and I get the sum, and the same with X and the first coordinate and the second coordinate. And so I can do this in either direction, right? So I can also add plus X here to also get to the same result. So it's pretty easy to see that X plus Y is the same as Y plus X, right? So these are so commutative, right? That's right. Okay. So I can so I can swap the order of these operations, and that's all fine. Okay. 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 So to do a so multiplication, matrix, so product, multiplication has so it's a little bit more complicated than addition and subtraction. And there's one general rule I will write down, but then there are a bunch of special cases of this general rule that kind of give you a lot of intuition and structure of what is going on here. So let me start with the general rule of multiplication. If you know this, you're going to know kind of everything you need to know about it. But it's this heavy notation version of things, right? So if I have A, which is in N by D, and I have B, which is going to be in D by M, right? Now they have different, they're in different spaces here. One is N by D, one is D by M. Those are, the D is the same, but the N and M are not, right? Then I can write a matrix C as equals to A times B. Okay, if I multiply, so two matrices, I'm not going to write like a times in them or a dot. Those sometimes mean other things. I'm just going to put them next to each other. Okay, this is the standard way to write it. Sometimes we'll get, you know, an algorithm will be a long chain of matrices that you just write next to each other so in some cases. And that means you're multiplying them so one after another. Okay, so I can multiply them, I put them next to each other, and so this is defined by the rule, okay, that elements of Cij, I'm going to sum over k equals 1 to D, and it's going to be A, I, K times element B, K, J. Okay, so this is the whole rule of multiplication. It's kind of, okay, what's going on there? All right, this explains everything, but it also hasn't really given intuition about so much anything that's going on here. All right, so a couple things to understand here is that C, what is the space of C after I've done this multiplication? I haven't said that yet, but you can maybe figure it out. What did someone say?
N by M.
So yeah, great. N by M. The D has disappeared, right? So it's a different dimension than either A or B. And so this, all of a sudden, like with addition, things just had to be the same dimension and everything stayed the same dimension. And that was nice and easy, right? Now that I'm doing multiplication, the dimension of the space is changing, and this can be a bit so confusing. And in order for this to work, I needed that this D is the same in both, right? That I need the A of N times D to be the same as the second dimension of A needs to be the same as the first dimension of B. That's because I'm summing over the second dimension of A and the first dimension of B, right? These all show up the same. In order for this sum to work, then I have to have so this dimension the same, and I can take values in the first dimension of A, N, right? So this I can take values in N, and the J can take values in M, right? So that's how so these different dimensions are kind of happening here. Another way of, I like to draw this as a picture of so like a rectangle. This is A, and this will be B. Okay, so this will be number of rows in A is N, number of columns is D, number of rows of B is D, and the number of columns is M. And this is going to result in a matrix C, and it's going to have the same number of rows as A and the same number of columns as B. All right, so this will be C, it'll be N rows and M, so columns here, right? Matrices are always kind of like this, implicitly the shape of like a rectangle. So it often helps to kind of draw them, I find, as rectangles to kind of make sure that the operations make sense. and that you have like the right dimensionality here. Again, these dimensions kind of along here and here have to be the same. And those are so disappearing here. And another way of thinking about what's happening is what is this choice of K, right? So if I choose this sum over these K things, that corresponds with the kth row of A. So, no, that's not, sorry, the kth column of A, right? And the, no, yeah, the kth, sorry, the kth row of A, right, which is of length D. No, sorry, that's the the ith column, sorry, the ith row of A, right? So this is I, right? And I take this with the jth column of B, okay? And these are going to wind up, if I look at the ith, so the ith row of C and the jth column, it's going to correspond with the entry here, right? So this entry will be Cij, right? So that is this column and this row, right? It's going to be combining together the ith row of A and the jth column of B here. Okay, it's going to give that element Cij, and this is going to be the Cij, this value here. Right. So okay, yeah. So this is matrix multiplication, right? So I think I promised to try and take a small break, and I want to break here. And when we come back, we're going to do my favorite mathematical operation. So hopefully that's enough to get you back after the break. But we'll just stop for a couple minutes and let you stretch your legs and mind a little bit. You're welcome to come ask me questions or whatever. Notation. Yeah, the notation is very important. If you write it a different way, as long as it's clear, it might be okay, but this is the notation I will use and the book will use and the homeworks and quizzes will use. So I would recommend to use this notation. This is probably the most common notation in the literature. If you look at modern machine learning and data mining papers, they're going to typically use this notation. Some papers sometimes use some different notation for various reasons. Oh, a smaller case C? I recommend for matrices, I will always use an uppercase. I will try to always use an uppercase, and for vectors, I will try and always use a lowercase. And that will help me kind of distinguish what's going on. C, it looks the same, smaller and uppercase, but I'll try and write it bigger. So some letters, it's hard to tell, but for A and B, which would be an M, these will be the most common letters for matrices. Then we will use uppercase, and you'll be able to tell because the letters are structurally different. Yeah. So maybe let's so get back to the lecture. After I get rid of this, okay. And get rid of that thing. So great. So okay. So if you know matrix, so multiplication, there are a number of special forms of this. We're going to see how you multiply a vector times a matrix or a vector times a vector. They're all just special cases of this, as it turns out. So if you remember this formula, you can derive all the other things that we'll want to do. But if you these things are nicer to have their own kind of notation and own way to to think about these operations. Okay, so kind of the first thing we'll start with is a vector product. Okay, and there are actually two types of vector products that you can do. All right. Actually, before we do this, let me actually I want to say, God, there are a couple more things I want to say about matrix multiplication. Sorry. Matrix multiplication is it's going to be associative. Okay, so if I can write A times B times C, right? And by the order of operations, you start from left to right typically. So that's A times B first, then times C. This is going to be equal to A times B times C if I multiply B and C first. Yeah. So this seems okay. So this is sometimes actually quite so useful for a few reasons. The runtime to compute these actually is going to depend on kind of the dimensions of these first. And sometimes what you'll do is that the cross dimension between A and B that they share, that's in the middle, if that's very large, then by multiplying them first, I'm kind of collapsing it, and the dimensions are going to be smaller afterwards, and then it's faster to multiply by C, where if I multiply B by C first, I'm going to generate a very large matrix, a large dimensional matrix, and then multiplying by A is going to be slower. So sometimes from an algorithm perspective, I want to choose the order I want to do this. From a numerical perspective, this might matter as well. We'll talk about numerics a little bit in the context that, again, I think I mentioned this earlier in the semester. If you run into numerical issues in your data analysis, you're probably doing something that's not very so robust. So you should, if you're getting numerical issues, don't just necessarily fix the numerical issues and say, okay, I'm happy with it using fancy techniques from scientific computing, but you should probably try and rethink what you're actually computing, because that's the answer isn't going to be very robust to noise in the data. Okay, so associative, this property it has a distributive property, right? So this means that I can do A times B plus C, right? So this is, we know how to add matrices, we know how to multiply them. This is going to be equal to A times B plus A times C. All right, so I can factor the addition through this multiplication. Okay, but it is not commutative. Okay, so if I have A times B, this is not generally equal to B times A. Right, there'll be some special cases we'll see where this is true, but in general is not true. And it's even worse than just not true. If I can multiply A times B, I can't even always, it's may not be a legal operation to do B times A, right? So if A is in our N times D, and B is in our D times M, and I have that N not equal to D not equal to M, right, and N not equal to M, right? These are all kind of, if these values are all different, I can compute A times B, that's fine, but B times A is not so it's not a legal operation. I can't, it's not defined. It's like undefined behavior. If you try and do it, your kind of library you use to do linear algebra should throw an error. Okay, so you have to be careful about the dimensions, and it's not commutative. You can't swap these things. Okay. One more thing before we do, vector multiplication. I can do a scalar matrix. So product. Okay, so often if I'm dealing with vectors and matrices and scalars, remember a scalar is going to be an element of R, just one-dimensional value, and I might have a matrix A, which is R n times D. I can multiply A times alpha times A. Often, then I'll use the scalar value will be I'll just use so like a Greek letter. Okay, if it's just a scalar, I'll use a Greek letter to describe that, so to kind of distinguish it from a vector. And then the multiplication, again, you just put them next to each other, and the result is going to be alpha times A11 up through, in general, alpha times A n D. Right, so I'm just entry-wise multiplying the scalar through. Okay, so I'm just scaling everything in the matrix. Okay. Okay, so vector products. Okay, so again, there are two types of so products here, I will use X and Y, and if I, these are both in so RD. The first kind of vector product is the most standard one, and the vectors need to be the same dimension. Okay, and remember, these vectors, I can think of them as 1 by D matrices or D by 1 matrices. And so if I know how to do matrix multiplication, I know how to do vector multiplication. Okay, but now I'm going to think of them as, so for some of this notation, I'm going to think of these as, so column vectors, okay? And I'll use notation so I don't need this, but some notation I will need this, and then we'll talk about the inner product. We will call the dot product. Okay, these are the same, means in this class will mean the same thing. Okay, and this can be written in several different ways. I can write X transpose Y, right? Okay, so the idea, if they're column vectors to start with, X transpose is now a row vector. It's now a 1 by D row vector, and Y is a D by 1 row vector. Okay, so I can write this as X1 up to XD times Y1 up to YD. And then I can apply matrix multiplication. These are just very skinny or thin matrices. And what do I do here? I write, well, I iterate I equals 1 to D over the same dimension that they share times Xi, so Yi. Okay, so I'm taking the same element, the first one from both of these, right? And I'm multiplying those together, and I'm adding, and then I'm adding up the result of all of these. Okay. In fact, if you remember, this is exactly the same thing that gave us in our matrix multiplication. Again, I took a row and I took a column here, and I ended up getting a single value at the end. And it was summing up all the contributions together. This is the same thing as this sort of inner product. Okay. Okay, but so how I'm going to write this though for the rest of the, hopefully for the rest of the semester, is this notation that I like better. Is just these so pointy brackets are these angled brackets, X comma Y. And the reason I like this notation better is because it does not require caring about the column or the row vectors, okay? This one is more common. The X transpose Y is going to be more common. You'll see this a lot in machine learning papers. This is something you do a lot in machine learning, and this is probably the single most common operation you see that's inside of, all of backprop and everything that is most of this CPU hours is just vector products, inner products. And you see it written like this, but I like this notation because I don't have to worry about the transpose or the column or the row vectors. I just take two vectors, the same size, and it's an inner product between them. You write this as in LaTeX / L angle, X comma Y / R angle. So you have to write the L, the left and the right angle. R angle and L angle. Okay. So this is the notation that I like because it gets rid of this other kind of stuff thinking about the transpose. All right. So the dot product, this is my, my favorite operation. Let me just say, you can also, so because it is one reason is that it is so because it's you can view it as a matrix so operation. It is so associative. It is so distributive, but it's also so commutative, because they have to be the same dimension to apply this. I can swap the order. So this means that xy is the same as yx. Okay, so I can do this now with the dot product. I can swap these around, and sometimes I might accidentally swap them, but it's not going to matter in this case. With matrices, you have to be more careful, but with vector multiplication with dot products, it's not going to be as important. Okay, and so for instance, with the scalar, I can write. So I can do something. For example, I can do alpha x dot y z. All right, so if alpha is a scalar, x, y, and z are vectors. Well, one thing I can do, I can factor out the scalar. Okay, this is like with expected value, we could factor out a scalar value. And then we can also make this so I can distribute the y plus x, right? So I can do alpha times x dot y plus x dot z. Okay, so I can So I can kind of factor stuff out here nicely. So this is really nice to work with. A lot more with matrix multiplication. There's a lot of, because of the lack of the not having the commutative property. Sometimes stuff you think will work with just scalar values. You've been doing scalar algebra, so not your whole life, but probably for 10 years now, right? A lot of the stuff you've been doing with scalar algebra, multiplication, addition, that works with vectors a lot of the time, but not often with matrices. The lack of commutative property with matrices causes some things unintuitively to not work. And I have banged my head against the wall kind of many times because of this issue. Like, this should work, I should be able to do this, and then in your head you are accidentally applying the commutative property, and everything broke. So with vector with the dot product, this is pretty nice. You don't, things are usually work like you expect them to from a sense of algebra. Okay, but why is this my favorite operation? One is because you get to do all these nice things. But the second is that it has a really nice geometric interpretation of what's going on. Okay, so let me show you this with an example. And this example will be important in many kind of things that will come in the next part of linear algebra, and then in kind of a lot of the actual data analysis stuff we actually do. Okay, so I'm going to get an example with two vectors. The first one, let me call this as, u, and I'm going to choose this carefully at 3/5 and 4/5, right? So it's a two-dimensional vector here. Okay, and I'll explain why I chose those coordinates a bit later. It doesn't have to be these particular, but these will be nice ones for this example. And then the other point will be, this is less important. This is v, so u and v, 2, 1. Okay, and I'm going to think about what happens when I take the dot product of u and v in this case. What's going to happen here? Okay, and so the dot product of, and I'll try and write my u's and v's distinctly here. U and V, the dot product. In this case, there's going to be a special way I can write this with the dot product. It'll be the length of U times the length of V times the cosine of the angle between U and V. Okay, so there's going to be an angle theta here between them. Okay, if I take the cosine of the angle, I'm going to, it's going to be the length of U times the length of V times the cosine of the angle. Okay, so why is it interesting? And well, the length, we will replace this with like a norm. This will be the start of next lecture. So this will be the norm of U times the norm of V, you know, okay. So those lengths will become less mysterious so that means. But in this case, I chose vector U, so its length is equal to 1. So the length of U is exactly equal to 1. The distance from the origin to this point with these coordinates is going to be equal to 1. Remember this, we'll talk a bit more about this next lecture, but it's the Euclidean distance. So I square these two things and I add them. 3 squared is 9, 4 squared is 16, 9 plus 16 is 25, which is exactly what the denominator is. So the length of this is 1. When the length of one of the vectors is 1, and we will often enforce this, then you can interpret this as, you can think of as a line going through this vector. Okay, so I've got this line that extends through U. And what this dot product is doing is I'm finding the closest point on this line. Okay, I'm making, and this is going to be a right angle from V onto this line. I'm going to call this the projection of V onto U. That's what this point is going to be. This is the closest point onto the line through U. Okay, and what the dot product is going to do is the U dot V is going to be equal to the length of the projection of V onto U. So it's this length here. This length here is going to be equal to the dot product of U and V. Okay? Yeah.
If you switch V and U, it's still the same product.
It's still the same dot product. This interpretation is not necessarily the same. Right? It worked because U is going to be a unit vector. If I project U onto the line through V, this length is different from that length.
Yeah.
Okay.
The dot product's the same.
The value is the same,
But
right?
Okay, so this interpretation only works if U is a unit vector.
If U is a unit vector, if one of them is unit vector, I can think of it as projecting onto the line through that vector. Okay, so I get this really nice geometry. Yeah. Yeah, so orthogonal, we'll talk about orthogonality more. I just wrote, like, if you've taken a high school geometry class, you might say a right angle. You put like a square like that to indicate it's a right angle, and that's what I'm doing here. Oh, here, yeah. So this guy, this is a pi. I'll use a pi to represent a projection. Yeah, thank you. Yeah, pi will be my symbol for projection. Yeah, we'll talk more about projections kind of in the dimensionality reduction part of class, and we'll go through this much more. But so this is kind of a preview of that. Okay, but I get this really nice geometric structure with the dot product if I have a unit vector. Sometimes I can, if I don't have a unit vector, I can still do this. I can factor out the scalar that describes the length of U, do the projection, and then rescale it. I can recover this point. I can actually recover this, this point. I can say pi of v onto u is going to be v, which is, or sorry, u, which is a unit vector, right, times the scalar, the norm, or is the dot product, u dot v. So I can multiply the vector u times the scalar, and that will give me this point. I've taken this point, which is of length 1, and I've stretched it out until it hit that green point up there. Okay, so I can actually recover that actual vector, right? Pi sub u of v is a vector, and its length from the origin is the dot product. Okay, so this is cool. This is, we'll see this more, but this is just kind of your first in this, and this will be a really important operation that we will use to understand high dimensional data when we want to say reduce the dimensionality or some other cool stuff we'll be doing. Okay, I have a couple more things I want to say. They're not going to be as kind of I don't think they're going to be as cool as that. That's my favorite operation. But let me quickly say, if we have, I told you there were two vector products. The other one is so that one was the inner product. This is the the outer product. And here again, I'm going to have x, which is going to be an r n, and y, which is going to be an r d. Okay, these do not need to be the same. They're going to be, I'm assuming that these are going to be, these are going to be, so column vectors here. Okay, and then I'm going to write x, y transpose. Okay, so I'm transposing y, right? So this is going to be a column vector, x1 up through xn, times y1 through yd. Okay, they weren't the same, but that's okay. They're both matrices, and one of the dimensions is 1. And that's the part that I'm going to use as the same. Right, so this is going to end up being a matrix, right, where this is x1, y1, x1, y2, up to x1, yd. This is x2, y1, and this will be xn, yd, right? And this will be an element of r n times d. Okay, so I can turn two vectors. If I multiply them as an outer product, I get the result is going to be a matrix here. Okay, so this is far less common, although it does occur in a few places. I think it will come up in this class, maybe once or twice. Okay, but I can make them as an outer product, and there the dimensions don't need to match, right? These dimensions, don't have to be the same, because I'm not using that. I'm using that the implicit 1 is the same. Okay, and then one last thing, matrix vector product. Okay, so this is also a really common operation, and it's again just a special case of matrix product. But I'll have a matrix A, which will be an n by d, and I'll have a vector x, which will be in rd. Okay, and I would like to do y equals a times x, right? So what dimension is so is y going to be? Is y going to be a matrix or a vector or a scalar? Yeah, so it's going to be a vector. It's going to be an n-dimensional vector. Okay, I've gone, A was n by d. I'm doing a matrix vector product, but really I'm treating X as a d by 1 matrix here, right? So I think of it as secretly as by 1, right? And so then these d's are the same, and I can multiply them. Okay, and so I like this is a case where I like to draw a picture here. Y equals ax. I think of this as a1 up to an, right? I have all these row vectors, right? Each of the row vectors, each in A, each AI is going to be in RD, right? They're row vectors of length d-dimensional row vectors, and then I'm going to have X here. This is X, the row vector X, which is d dimensions, right? So it doesn't line up with the rows, but I'm going to kind of twist it and then have it multiply by each of these by each of the rows in A, right? So I'm going to, the output is going to be A1 dot X, A2 dot X, up to AN dot X. Okay, so if I look at A2 here, I'm going to take a dot product with X, right? So I took X, I kind of turn it sideways when I multiply it, and then for each of the rows, it's going to kind of go across into this value. And this is a scalar value, right? So then that's why this is going to be in Rn, because there are n different rows of A. Each of them is a result of a dot product. And if you look back at the matrix multiplication, what was here, what is each of these operations doing? Each of the row times the column, they're both d dimensions. I'm combining them with the dot product. So I'm getting a scalar out here, right? So finally, I can see that this is equal to AI dot BJ, right? This is a dot product again here. Okay, great. So we'll stop here, and we will talk about kind of norms and how to do more kind of and stuff like inverse, which is like the division for matrices.